We're now scouring these planets for evidence of atmospheres, liquid water, and life itself.
We are going to know where in the night sky you can point and find another Earth.
We have a scientific method to actually determine whether there is life on another planet.
Another Earth. Alien life? The truth is out there, but are we ready for it? The Earth gives us the blueprint for life as we know it. The sun warms our oceans, creating the perfect environment for all scales of life, from the very smallest to the giants that eat them. Mountains, plains, and forests teem with plant and animal species. And it's all cocooned in a thick atmosphere that nurtures and protects. For us, it's paradise. 20 years ago, a group of scientists decided to find out if there were other paradises out there, so-called exoplanets, orbiting the stars that light up our night sky.
Just in the last decade, we've had this explosion in the discovery of these exoplanets, which has revolutionized the whole field of astronomy.
The early days of exoplanet hunting turned up enormous Jupiter-sized planets by the boatload. These hot, gassy giants proved easy to find, but hostile to life as we know it. Now, though, new telescopes and technologies have allowed astronomers to target smaller planets, Earth-sized ones, and the stunning results have transformed the way we see our place in the universe.
We now know something precious, that our planet Earth is not unique. It's not even rare. There are tons, hordes, flocks, if you will, of other Earth-like planets out there fluttering around the other stars. Some stars probably have multiple Earths orbiting them. That's how common Earth-like planets are.
We owe this exoplanet explosion to a space telescope called Kepler.
The Kepler Space Telescope is an observatory in space that is staring at one spot in the sky. It's looking at roughly 150,000 stars, and it's looking for the telltale sign of planets orbiting those stars. Then every time the planet passes in front of the star, it'll block a little bit of that starlight. And if you plot the amount of light you get from the star, it drops and then goes back up as the planet passes.
In just 4 years, scientists have detected over 1,000 exoplanets just from their shadows. But Kepler has a problem. It can't tell if the shadow is made by a giant gassy planet hostile to life or a potentially habitable Earth-like planet.
What we're measuring when a planet passes in front of its host star is what is the area of the planet relative to the area of the star that it's passing in front of. It's a ratio, basically.
But Jupiter-sized planets crossing giant stars fool Kepler, because they block the same fraction of light as Earth-sized planets crossing smaller stars. To prove a planet is Earth-sized, you first need to measure the size of its star using the world's biggest telescopes. But that's time-consuming, expensive, and it creates a huge exoplanet backlog. But astronomer Kay von Stassen has come up with an ingenious shortcut by turning the raw Kepler data into sound.
What the Kepler telescope directly measures in the data that we use is the small changes in brightness that a star produces due to the flickering arising from the boiling and roiling motions of gas at its surface. What we can do then is take that light flickering data and transform it in a sound studio, for example, into audio frequencies. And so then we can represent with sound what we're actually detecting with light.
The bigger the star, the more its surface boils with activity, making big stars flicker more powerfully. Converted to sound, this boiling becomes a deafening hiss.
Well, let's listen to some stars.
Okay.
Can we hear the red giant star, please? I'm going to bring up the volume here. This is a very large star, very low density. And so that large amount of hiss is the result of vigorous boiling and churning at the surface of this large red giant star. Can we get the dwarf star, please?
On smaller stars, sunspots dominate the sound profile, creating a low-frequency drone.
It actually sounds like a series of clicks. Krrrr.
But below the clicks lies the faint hiss Kayvan needs to size the star.
Underneath it, at a very low level, is a little bit of hiss. That little bit of s is actually the light flickering that we're interested in.
By accurately measuring the level of this background hiss, Kayvan can work out the size of the star. In this case, it's around the same size as our star, the Sun. Kayvan's work could be the breakthrough exoplanet hunters have been hoping for. It's cheap, the results are practically instantaneous, and once you know the size of the star, figuring out the size of the planet, casting shadows over it, is child's play.
It feels like a very privileged time to be a scientist, to be an astronomer working in this area and contributing to the hunt for the next Earth. Here we are actually discovering these worlds by the hundreds, and now on the cusp of being able to identify the next Earth.
Astronomers suspect there could be tens of billions of rocky, Earth-like planets in the Milky Way. Places where perhaps life has gotten a foothold. But life as we know it requires water. How can scientists possibly find this miracle substance on planets light years away? Water divides our living world. Those with it prosper. Those without suffer. Remarkably, the water we drink today contains the same atoms as the water dinosaurs drank 100 million years ago. It's the same water that formed clouds over the early Earth 4 billion years ago. And every organism that has ever existed on Earth has used this single ration of water as the biochemical powerhouse that keeps it alive.
On Earth, all life requires liquid water to grow and reproduce. It's the common ecological requirement for life.
Liquid water is just so good for getting evolution going. Molecules can dissolve in the water, actually interact with each other, form more complex chains.
It does it with charge. There's positive charges and negative charges separated between the hydrogen and the oxygen in H2O. Those charges break apart the hydrocarbons, the carbon-based molecules that persist everywhere in nature.
Now that's very rare. Hardly any other liquids do that. So liquid water is a natural starting place when you look out into the universe and say, what planets could possibly have life?
To understand how much liquid water is out there, astronomers must first calculate how common water is in all its forms. Amazingly, they find it everywhere they look.
Water is incredibly common. In its gaseous form, we see water vapor filling the space between the stars. We see it in clouds of material that are actually forming new stars and planets right now.
Since water is a fundamental building block of stars and planets, exoplanet worlds must surely have it in abundance. But if you're looking for life, you need to find liquid water.